recording this as the test review, and I'll come talk to you about that. What's that? They will be. These I have to upload now. It used to be that they was just streaming on there. Yeah. So yeah. For example, so this will be on Google Plus, but you know. Oh, they're on my other account. Here they are. So they're also on like. So they're the only thing in the channel for this account. So it's called George Raber, but it's not my. I actually have two Gmail accounts. I don't know if that's something they're going to get mad at. But GHY.GIS at gmail.com is this one. So this is GHY 210 week 3. So this was back when it was allowing me to stream it on there. So see, here I'm talking about this. Really an infinite number. So that was just last week. So that's last week's lecture. Okay. All right. Yeah. Stop that.
What's the date for this test we're reviewing?
The test is next week, the next class period. In fact, I will only be here for the first about half hour of the class period, and CAs will administer the test on both campuses after that point.
This upcoming Thursday?
Yes, this upcoming Thursday. We won't have a lab next week. That's correct. Just the test, and the class will be over. So, it like I said, it's about 23, 24 questions, I think. Yeah, 24 questions. Right now, I mean, I may take a question off or add a question. I was writing these up, modifying it from old tests last night. So that's where it is right now. So I'm not gonna say it's definitely 24 questions, but it'll be around that. And most of them are short answer, but there is a few multiple choice questions. Okay. So you don't need to bring a Scantron or anything. And we're going to go through what you need to study for. And what I would suggest that you do is you go through and you make sure that you understand these concepts. And then if you do need more, either go back and look at the lectures, or go read those parts of the book again, or both. I'm gonna make this. Let's see, make it big. Oh, there we go. All right, so this is the first part. So basically, it covers the last 4 lectures. It's going to cover everything, including what we talked about today. Okay. The very first week, we kind of introduced the course, but we spent some time categorizing different types of maps. We talked about reference maps versus thematic maps. Reference maps are basically maps that help you orient or find something, okay, in space. Usually your own position, but sometimes it's just in general, where is this thing, okay? That's a reference map. And sometimes a reference map can be part of a thematic map, but it's usually not the main emphasis. It's just the reference information is helping you get your bearings. And then the thematic map is the thing that's trying to tell a story, trying to communicate an idea to you. So that's the difference between a reference map and a thematic map. And so you need to be able to know that difference. So a reference map is for referencing location, finding location. Thematic maps are for telling a story or communicating an idea, communicating a variable to people. Okay. So what would be an example? Like, most of the, just by default, what you see on Google Maps is mostly a reference map. Okay, now if you turn on the traffic layer, that's a thematic element that's on there. So that would be a thematic map. Or a map of population density is a thematic map. Or most of the maps that we've talked about and shown as examples in this course or thematic maps. All right. And then something that we did talk a lot about today is the difference between qualitative and quantitative. And we did talk about it back then, but you may not have fully understood it until today. So a qualitative map basically shows you information about things that are labeled names or categories, whereas a quantitative map communicates quantities or numbers to somebody. So you can map the same thing qualitatively and quantitatively. But typically you map quantities by showing gradations and qualities by just attaching different colors or symbols to those different qualities. So if you had cities and you showed them in terms of their size, larger the city, the bigger the size. Okay, that would be which one? Qualitative or quantitative? Got to be quantitative, exactly. Numbers. Okay. What if your cities were just coded as to whether or not they were they had well, you know the answer is going to be qualitative, but if they were coded based on if they had an NBC station in that city or not. Okay, that might be correlated definitely with population, but that's still qualitative in nature. It's just yes, they have that, or they don't. Or whether or not they voted Republican or Democrat in the last election would be qualitative, or whether or not they had a female mayor. That would be qualitative as well. All right. Whether or not they had a mayor at all. The type of government, there are like basically 3 or 4 different models of city governments in the United States. Some have city managers that run the whole show, and they have a mayor that's basically doesn't have power. Anyway, so you could have different colors based on which type of city government model that particular, and that would be qualitative. All right, so you need to either on the test you'll either need to provide an example or identify an example. Okay. All right. So we did talk about these concepts. These are the concepts of abstraction and generalization. Because remember, as cartographers, we're not symbolizing the entire world. The world is very complex. And so in order to abstract and generalize the world, we can do these 4 things. And sometimes the lines kind of blur between what they are. Okay? So I'm not going to ask you to say, is this abstract? I mean, is this selection or is this classification? That's not like that. But generally, you need to know what each of these terms means. So selection is the process by where we just select what we want to show. We're not showing everything in the world. So we're going to pick a thematic element, and we're just going to show that and maybe a little bit of reference information to help people know where they are. So selection is choosing those elements that you want to put on your map. Classification is the process whereby you make the complex world more simple by grouping things together. You show all the roads using the same symbol, or by using 2 or 3 different symbols for different road types. Or you show, like what we did classification today, you show the variability in population by dividing it up into different classes, or income, or fertility rate, so on. All right, simplification is the process where you take a complex feature in space and show it as something that's simpler. So this could be something like taking the city of Hattiesburg and just showing it as a dot. Is the city of Hattiesburg a dot? No, it's actually got a boundary. But on most maps that are very small scale, in other words, large area maps, you just want a city as a dot. Or the boundary between Mississippi and Arkansas. Lots of maps will simplify that a lot because it's very complex river meander. All right, symbolization is the process whereby we choose a symbol for a particular thing that's in space. Like how are we gonna symbolize it? And sometimes this is the one that's kind of the most related to these other ones, particularly classification. Symbolization is choosing a symbol for an object that may be related to what class we've chosen. And symbolization itself is a method of simplification. It's choosing a symbol for an object. It's also the easiest one to think about, because of course we symbolize things. All right. Okay, you need to know the elements of a map. We talked about what those were, a title, the actual data itself, okay, the map itself. Sometimes it's called, ArcGIS calls it a data frame, but lots of times it's just the map. The title, the map, the legend. Okay, there's always a legend. There's some sort of orientation mark. Sometimes it's a north arrow. Yes, the compass rose would be that. The line. What's the line that goes around the edge of the data? What's that called? What? Neat line. Yep. It's called a neat line. That's one of the ones that's lower in priority, but you still need to know what that's called. And scale. The scale of the map is important in most cases. What's that? Yeah, so all that falls into the category of metadata. So any other information about the projection or who created the map or all that, that is referred to as metadata. So any labeling that's not a map label is referred to as metadata. And so that's one of the elements of a map. META data. That would be part of metadata. Technically, metadata means data about data. So it's data about your map. All right. If I had a map that didn't have, if I showed you a map that didn't have like a scale, the maps that I show you are going to not have obvious things, like not have a legend. And then you would say, well, it doesn't have a legend. That's one of the important elements of a map, or a scale bar or something like that. All right, now, scale, ways of displaying scale on a map. So there's a question that basically talks about how there are 3 different ways to communicate scale on a map. One of them is it's probably the most ambiguous, because remember, at one slide I called it a written scale, one slide I called it a verbal scale. Okay? So there's that way, and it's usually written out, 1 inch equals 5 miles, or 1 inch equals 10. That's a verbal or written scale. I don't care which one you call it. There's not a multiple choice question where one's verbal and one's written. There's no trick question in that regard. So no one or the other of those terms. The other one that probably should have talked first is just the most simple way of doing it, and that's communicating the scale as a representative fraction. Okay, but it's important that you know that when somebody puts the representative fraction on a map, like 1 over 100,000, you don't have to ask what, 100,000 what, okay? It's 1 whatever over 100,000 whatever. It's a fraction. So 1 inch on the map is equal to 100,000 inches. But we're talking about scale here. So the size of the map relative to the real world size of those counties.
Oh, so like a world map, where you're trying to map out the entire world, how they have to stretch it out over a certain region, it's low. They have to certain countries bigger than they actually are. Like Antarctica, for example.
That's when we're talking about projections and coordinate systems. I'm just talking about how, like, if I have a map of the United States, and I have a map of just Mississippi, and they're the same size on the screen, okay? obviously I've shrunk down the United States more than I shrunk down Mississippi to fit on the screen. That's scale. So when you look at a map, it's important to communicate to the user, particularly if they're not familiar with the area that you've mapped. It's important that you tell the user what the scale of the map is. So like if I was doing a thematic map of Hattiesburg, it'd be really important for me to put scale on there, because outside of our town, there's not a whole lot of people that really know how big Hattiesburg is, right? Like if I went home and said, hey, I made this map of voting patterns in Hattiesburg, Mississippi, if a lot of my buddies back in Orange County, California, they don't know, like, is Hattiesburg, is as big as this hometown that I'm in, or smaller? Or, they might want to know that. And so it's important to put a scale on the map that communicates that. It says something like 1 inch on this map is equal to 10 miles in real life. That's one way to do scale. That's a written or verbal scale. Another way to talk about scale is as a representative fraction, 1 to 10,000, meaning that any unit that you measure on this map is equal to 10,000 of those same units in real life. Yeah. So ratio, representative fraction are also interchangeable words. So sometimes you might see it written like this, 1:10,000. Okay. Sometimes you might see it written like this, 1:10,000. Okay. You can see it written either way. Those are both equivalent statements. All right. So, by the way, if I had one, this would never happen, but if I had one that said 1 over 5,280, what that means is that 1 unit is equal to 5,280 units. So, what that means is that 1 foot on my map is equal to what? Right. So, I could have 1 to 5,280, and then I could also write below that 1 foot equals 1 mile, and that would be showing both it as a representative fraction and showing it as a ratio, or I'm sorry, as a written or verbal ratio or representative fraction. Okay, and then the last way to show scale on a map, which is probably more common than those other two, is just as a scale bar. A scale bar is a graphical representation where you're just basically showing this equals this much. The nice thing about that is people can actually, like, okay, well that's 100 feet, and they can go on the map and say, oh, that's about 300 feet to get there. Okay? And in reality, there's oftentimes at least 2. On lots of maps, sometimes they'll do 2 or 3, maybe sometimes all 3, but they'll put more than one way to go on there. Most thematic maps, it'd probably be overkill to put 2, but most reference maps will have at least 2 ways. But that's not on a test. So you can talk about that. Okay. Now, it's important that you understand. Oh, I almost skipped over graticule. What's a graticule? A graticule is when you put the latitude and longitude lines or the reference marks. It could be northings and eastings on the map. So it's lines on a map. So lots of times on world maps there are lines on the maps, and they just represent latitude and longitude. But if you put lines that represent a coordinate system, which we'll talk about in the next section, that's a graticule. Okay. Large scale versus small scale. It's important that you realize that a large scale map is a map that's closer to 1 over 1, because that's a larger number. However, a large scale map shows less things on it. Less of the world. Small scale maps show more of the world because the number represents, the representative fraction represents a much smaller number. That's why they're called small scale maps. So the scale itself is small, which means it's showing a large area. So you need to know that relationship. Small scale maps equal large areas. Large scale maps equals a relatively small area. And they are relative terms. I mean, it's a map of campus. Nobody would probably argue that that's a large scale map. A map of the United States, nobody would probably argue that that's a small scale map. But in between, who knows where the boundary is? I don't have any test questions on, is this a small scale map? But the test questions are relative. The test question is relative. Okay, which one is the larger scale of these two numbers? Okay, and if you need to break out your calculator, I'm fine with you using a calculator, but you know, if you don't, that's fine. But the question may, you know, involve two different representative fractions where you have to specify which one is. So the way you answer that question is to find out which one is the larger number. So 1 over whatever versus 1 over whatever, which one is the larger number? That's the larger scale map. Okay? All right. Okay, so projections and coordinate systems. One of the things that you need to know is yes, I did put it on there. Y projections. But what I mean there is, why are map projections necessary? If we go back to that lecture, the reason that map projections are necessary is that we want to be able to measure areas and distances on our map. Okay? And we can't do that without map projections. We need to be able to take the world and put it on a flat surface and still be able to calculate those values. So we might be more interested in calculating relative areas, and there are map projections that are better for that. And you don't need to memorize specific map projections, by the way. There are map projections that are better for measuring distances, things like that. Okay, so basically what I mean by there, so what is lat long measuring? Angles. But most map projections, well, all map projections are in some linear unit. So that's what you need. You need to know that. Okay, projection issues. What's compromised in a map projection? Well, the main compromise that we went over when we gave that lecture is this compromise of shape versus area. So we're going to start messing up the shapes a lot, or we're going to start messing up the areas a lot. So sometimes people refer to that as a conformal projection versus an equal area projection. An equal area projection is weighted more toward area. Conformal is weighted over in terms of the true shape. Now, conformal or equal area? Equal area or conformal. Sometimes, and I think the book is like this. It's been a little while since I read that chapter. They'll also talk about, basically they'll say that some map projections distort area, which we covered, distance, direction, or shape. But those two middle D's, distance and direction, are really distortions that can be boiled down to the trade-off between shape and area. Okay? Because if you start messing with the shape, you've got to be messing with distances and directions. But there's no test question that says distance and direction. Okay? I kept it like the lecture where I talk about the trade-off between shape and area. Okay. However, there is a question on the general types of projections: cylindrical, conic, and planar. So basically, those talk about the shape of the developable surface. So did we wrap a flat surface around the globe and project the globe onto the flat surface that was wrapped around the globe? Or do we wrap it around like a dunce cap that's conic? So wrapping around the globe is cylindrical, dunce cap is conic. Planar means we just took the surface and stuck it to the side of the globe and projected it onto the flat surface. So like the world from space that you did in the lab is planar. Okay. Conic is dense cap, and the most common use of a conic projection is for maps of continental size areas, like North America and Asia. They also use conic maps for the state plane coordinate system for states that are wider than they are tall. Cylindrical maps are used for the Mercator. The Mercator projection is the most famous cylindrical projection. And the Mercator projection is used first as a worldwide map for navigation, and it's also used in its transverse form for mapping small areas of the world. We don't map the whole world using the whole world at the same time using UTM. We only map anything that fits in those UTM zones entirely within a UTM zone can be mapped using the UTM coordinate system. If it doesn't fit entirely within the UTM zone, then the UTM is a bad choice for those maps. All right, but that's all that stuff about the UTM zone on there. But you might be asked for a specific example of a projection, a conic projection, a cylindrical projection, or a planar projection. So planar projection would be like the world from space through orthographic projection. It means that the developable surface is left as a flat surface and the world is projected onto it. So you usually only see at most half of the world in a planar projection. Yeah, I mean no, it's not in the math. You're right. It's not in the mathematical projection. So I don't even have any questions on the mathematical projection. So it's always cylindrical, conic, or planar. Yep. Okay, what is needed to specify a projection? So a projection, we spent a lot of time building up to this, but we remember we talked about the shape of the Earth. So you need to have a model of the shape of the Earth. And we referred to that as a mathematical model of the shape of the Earth is called a spheroid. Okay? So you need to have a spheroid. You need to have a method for attaching that spheroid to the Earth, to the actual Earth, its tie point. And that is referred to as a datum. So a spheroid, a datum, and then if it's actually a projection, if it's not latitude and longitude, you also need to specify the developable surface, whether it's cylindrical, conic, planar, and then finally the units. So there's 4 things if it's an actual projection. If you're doing latitude and longitude, you only need those first 2, spheroid and datum. If you're doing a projection, you need to specify the developable surface and the units on top of that. And there's lots of things to specify inside of the developable surface, like where the origin is, and if there's 2 lines of tangency or 1, there's no questions on the test about that. So if you know those 4 things, and generally what they are, then you're fine. So spheroid, datum, developable surface, and units. Developable surface. Technically, if you wanted to be complete in your answer, you might say something like the developable surface and how it's tied to the Earth, how it's tied to the spheroid, but you'll get full credit for just saying developable surface. Okay. What is a projection on the fly? This is not covered that well in the book. This was a question that was in the labs, and we did talk about it at the very end of lecture. Remember when I was saying, okay, well, you can have this data that's in projection A and this data that's in projection B, and when you show them an arc map together, they'll show up together. It'll actually put them together and overlay them correctly because ArcGIS does projection on the fly. In other words, it can do the math to convert between projections, even if your data is actually in 2 different projections. So Projection on the fly is the ability of modern GIS software to convert two data sets into the same projection. And what it actually does is the very first data set you bring into your view, it uses that projection and converts everything subsequently, everything else into that same projection subsequently. The drawback of this is that if you do not specify the projection of your data, in other words, if you get some data from somebody and they didn't tell ArcGIS what projection it's in, then it really screws things up. And that's actually why, I don't know if sometimes I've probably told you, I'll just load it in, just load the data in. You get a warning that says, this data doesn't, there's no projection specified in this data. You want to continue? And I just say, yeah, click yes. The reason why I'm saying click yes is because I know that that data is in the same projection as all the other data that you're adding to your view. But if it wasn't, it wouldn't show up correctly because it doesn't know how to, it can't do the projection on the fly if it doesn't know what projection it's in.
You're saying the data that's being added has to already be in some sort of projection so it can be converted?
Yeah, unless it will assume that it is in the same projection if a projection isn't specified. So if you have 10 different data sets, you know that they're all in the same projection, you can ignore the warning. Does that make sense? Yeah, and then that's also where I said one of the biggest mistakes, or one of the biggest problems that I see young GIS cartographers doing is trying to load data in where they've told it it's in a projection. They've used define projection or project inappropriately, and they've basically told some data that it's in a projection that it's not in. And so you'll never get your data to line up until you tell all the data that it needs to be in the right projection. Now, all of that isn't on the test. What's on the test is what I said about projection on the fly. Projection on the fly is the ability of GIS systems to convert data and display multiple data sets from different projections in the same projection together. And that was a question that was in the labs. So if you go back and look at the lab for that week, but it's not really covered well in the book. That's why I hit that one a little harder than the other ones. Okay, so geographic data, which is just last week. So we're going, you know, we only have 4 weeks of information here. Okay, so here, what you need to know, I left this off. I need to go back and add it. Okay, I do have 2 different distributions of data. In other words, I have 2 short distributions of data, and I do ask you which column has a lower standard deviation than the other column. But I do even say you should not actually have to calculate it. So remember what standard deviation is. It is, you can think of it, it's not exactly this, but you can think of it as the average distance of the data away from the mean. So if I have a bunch of data that's let's say I have numbers that range from 1 to 10, but almost all the data is 4s and 5s. And then I have another data set where almost all the data is 1s and 10s. Which one has the largest standard deviation of those 2 data sets? Yeah, the 1s and 10s. On average, they're further away from the mean, which is probably somewhere around 5. Okay? So I don't actually have you calculate, so we won't calculate standard deviation. So you need to know, I should put this back in here, but you do need to know these terms. You need to know mean, mode, range, medium, outlier, and standard deviation. So those are the terms from the book and the lecture that you do need to know. Okay? And I'll go in and put that back up there and upload a new version. It'll also be in this video. All right. Now, when we talked about data, we talked about how we can have, what is geographic data? Well, geographic data is just data that has spatial information, and it can have a spatial dimension. What does that mean? Well, it's a point, which is 0 dimension, line, which is 1 dimension, polygon, which is 2 dimension, or it's a surface, which is technically like 2.5 dimensions. So, meaning that the surface can only have one value. That's why it's 2.5 dimensions, not 3. You can have three-dimensional data, but it's really not common in GIS systems as of yet. Okay? They're starting to get data that has like buildings and stuff in it. It's not that common. Okay, so that's the spatial information. Also, what makes geographic data geographic is that it has attribute information. Okay, so you need to know about attribute information. You need to know about data measurement levels, which were the nominal, ordinal, and interval ratio. There is not a question that distinguishes between interval ratio. So if you know the nominal means labels or names, ordinal means orders, high, medium, and low, interval ratio, those both mean that we're talking about real numbers where we can add, subtract, multiply, and divide from each other. Okay? And then in an attribute table, what do the rows and columns represent? The rows represent entities, things in space. The columns are the attributes of those things. Okay? So you need to know that. Also, in there, you should know that there's the data. In other words, there's a set of spatial coordinates associated with each entity, and there's the attributes that are actually stored in the data, but then we also, as cartographers, have to choose how we symbolize it. So even if we have a polygon that represents a city, we can change that polygon to the centroid and just show the center of the city. So there's how it's stored and also how it's communicated. So there's the symbol level, and the data level. The same thing with the attributes. We could have actual numbers, but we could choose to symbolize it as like high, medium, and low, which would be ordinal. So we've got geographic data. Geographic data is divided up into spatial information and attribute information. And then geographic data for us is actually divided into the data aspect, but then also the symbology or the cartographic aspect. All right, we talked about different sources of error. Here you should just be able to recognize and categorize different error types. So is that source error, is it processing error, or is it cartographic error? I do have a question on the difference between a ratio versus a proportion, and basically how to calculate a percentage or a rate, which is just, so if I say, how would I calculate population density? It'd be people divided by area. Or how would I calculate, if I had a column that represented elderly people and a column that represented total people, how could I get a column to represent the percentage of elderly people? Which is, you would divide the column that represented elderly divided by the total population. Okay. Then finally, choropleth mapping, which is what we talked about today. So this is the one that's most fresh on our mind. Hopefully we can get through this one a little quicker. So what is choropleth mapping? It's basically taking enumeration units and symbolizing them based on their attributes. Symbolizing the entire enumeration unit based on its attribute. Okay, when is the method appropriate? It's appropriate on derived data. So that's what I mean by that. That's a little vague, right? When is this method appropriate? You know, makes it sound like it might, I don't know. Anyway, that's too vague. When is this method appropriate? What I mean by that is that you should typically almost always use derived data, not totals. So you might have a question where you have to recognize that mapping totals is a problem in choropleth mapping. All right, now this data classification, we talked about it this week, so I threw it down here. It's emphasized here. So you need to discuss, I already went over this, but you basically need to be able to discuss the way that the question's set up is that you should come up with or remember at least three, well actually 2 or 3 of the classification methods, how they work, be able to describe how they classify, and that includes natural breaks. Like if you want to say natural breaks and the user basically chooses the breaks, that's fine. Or if you want to say you don't have to describe, like, just so you know, you don't have to describe the algorithm that Jenks uses, but it's a computer algorithm that picks the largest breaks. 3 of them. Yep, the test will ask you to describe 3 of them, and then to talk about an advantage and a disadvantage of each one. You may actually need to recognize, if I show 2 maps, and I say which one is more likely, one versus the other. So that's another question. So recognize that there's probably more variability in an equal frequency map than there is in almost any of the others. Okay. All right. Be able to discuss what distribution is. Okay, so I left it. I guess I left it off of there. Anyway, range, mean, median, standard deviation, mode, etc. What those are. And I said min max, so you should know what that is. Min and max, minimum and maximum, and an outlier. Outliers on there too. So, but anyway, that's the question that I meant there. Okay, you should know the difference between a disometric map, which I spelled wrong, and a choropleth map. Basically, one uses enumeration units, one uses cartography-defined boundaries. Okay, we're still coloring in an area on the map. That's the similarity. The difference is you choose your own areas to color in. Okay. All right, classed versus unclassed. Here it's important that you know that unclassed maps typically do not show boundaries, and the way that you create an unclassed map is you just create a linear scale through a color range or through a shading range. Okay, and then in general, you basically need to know that you don't want to go through too many color steps. Really more than 2, going through more than 2 colors in most cases is bad. And then in general, the advantages and disadvantages that I showed earlier. Okay, I'm going to stop the lecture, the video again.